Hello, I am Komal Dadhich, and today I will be presenting my research paper with Sri Channa Dagubati and Jaya Srivalasan titled Bar Chart Analyzer Digitizing Images of Bar Charts. We are part of the Graphics Visualization and Computing Lab at International Institute of Information Technology, Bangalore. In this work, we will discuss our workflow to digitize images of bar charts of various types and orientations using image processing based methods such as morphological operations as well as tensor field computation and analysis. In this presentation, we will walk through the problem area pertaining to the chart digitization and related work, followed by our suggested approach, different components of our workflow, experiments, and discussion on limitations before we conclude the talk. Visualization of data is an effective way of seeing the trends and summary represented in the data. Charts are a universally accepted form of visualization that has been discussed in the academic curriculum as well. Hence, charts are also the most frequently used visualization form due to their familiarity. Charts are usually embedded in documents such as research articles, newspapers, and magazines in an image format to display consolidated information without actually publishing the source data. Hence, data extraction from chart image becomes a relevant problem for performing tasks like summary generation and redesigning charts. Since the design space for chart creation is wide, in this paper, we mainly focus on bar charts, one of the most simplest and most commonly implemented visualization that has various subtypes like simple bars, grouped bars, and stacked bar charts to visualize the data in interest. The selection of the bar type is done based on the univariate and multivariate nature of the data. We also include histograms as per bar type based on the similarities between the geometry of bars and bins of histogram. The prior attempts with deep learning models communicate the limitations pertaining to stacked bar. Hence, our goal is to explore image processing based methods for exploiting spatial locality for object detection to localize graphical objects such as bars. In our work, we propose the bar chart analyzer, a semi-automated workflow that can extract the data from a given image of a bar chart. We combine image processing and computer vision based methods with machine learning models to classify the subtype of a given bar chart image and to capture text from the given image. Our contribution also includes extracting templatized text summary of bar charts from its source image and providing a training dataset to classify 7 subtypes of bar charts, including histogram. Chart classification and interpretation have been an interesting problem that has been explored by various implementations, such as revision and chart sense, to name a few. As one of the primary attempts in this area, revision performed text type classification using feature vector generated by the geometric property of text, along with mark type classification, also known as chart type classification, using a fine-tuned LXNet. ChartSense, as another implementation, uses GoogleNet to identify chart type, followed by connected components method to specifically extract bar objects in the given image. ScatterAct is a system that extracts data from particularly scatterplot images by mapping pixel to the coordinate system of the chart with the help of OCR. Automated data extraction for bar charts has been done by identifying graphical components and text region independently. Tensor fields have been used for detecting features in natural images, such as corners and edges. In our work, we extend the use of tensor fields for chart images as we refer to closed form solution for TensorFloat for exploiting geometrical attributes of bars. In our proposed workflow, we divide the task of data extraction into several components, such as classification of chart, annotation of image, tensor field framework, chart canvas extraction, etc. First, we perform chart subtype classification on a given input image using our convolutional neural network based classifier. The classified image is further annotated manually using the tool label image to localize and label chart components such as bars, text labels, and chart title, etc. The annotation actually helps in extracting the chart canvas and performing text detection and recognition. The extracted chart canvas is pre-processed through morphological operations to refine the boundaries of bars. The pre-processed canvas image is used as an input for the tensor field computation and analysis framework. BarChartAnalyzer generates the extracted data in a tabular format that can be used further for chart summary generation, reconstruction, or redesigning the plot. Chart interpretation is highly dependent on the chart type being depicted in the image. Similar to chart analysis, data extraction steps for a given chart image are specific to its chart type. Hence, we use a classifier to identify the chart type initially. A convolutional neural network with the VGGNet architecture is used to classify an input image as per its chart type. The classifier is a combination of convolutional layers, pooling layers, and fully connected layers, also known as dense layers. For an input chart image, we first resize the image to a size 200 x 200 and then feed it to classifier. The classifier provides the class or label for the given image. The 7 subtypes that can be identified by our classifier include charts with horizontal and vertical orientation of simple grouped and stacked bar charts along with histogram. Here we use positive semi-definite second-order tensor fields to detect bar objects by extracting geometry in BarChartAnalyzer. The tensor field is thus useful in localizing the corners of bars. For this, we need to isolate the region in the chart image, referred to as chart canvas, that contains the bar objects only, so that the tensor field is computed pixel-wise in this region of interest. We perform an interactive annotation using the tool label image to select the area of interest, that is chart canvas and text regions. The tool provides interface to create and adjust the bounding box around the area of interest and label for the selected area and saves the annotation in XML or text format. We particularly use the XML format to save our annotations for chart images. The XML file has information such as labels and coordinates of bounding box that helps us in selecting a specific region to extract chart canvas or the extracted text region for OCR. The coordinates of bounding box are stored in form of minimum and maximum XY values in pixel space. The chart canvas is then processed through morphological operations as a segmentation technique to remove grid lines and contour detection techniques to add clean border boundaries of bars. Our methodology involves determining a positive semi-definite second-order tensor field from a given chart image and using the tensor field topology for data extraction from the image. We first use structure tensor to exploit local structure. Structure tensor is computed based on the gradient tensor convolved with Gaussian filter and highlights the boundaries of bars. Tensor voting is the perceptual organization of information using votes casted by the local neighborhood. Here, to implement the closed form solution, we use the structure tensor as initial second order tensor Kj to start the voting process. We compute these tensor fields for each pixel of the image. The tensor voting aggregated tensor follows the Gestalt principle of perceptual organization. We use anisotropic diffusion with diffusion parameter value delta equal to 0.16 on this tensor to map it from the normal to tangential spaces. The probabilistic geometric classification of pixels computed using a 2D tensor field, that is structure tensor or tensor voting fields, is computed from the eigenvalues of the tensor at the pixel. The pixel is classified as degenerate point or critical point if it is a junction type feature. That is, CP value is nearly equal to 1 and CL value is nearly equal to 0. Degenerate points in tensor fields are points where the eigenvalues are equal to each other. Our goal is to find all the critical points in chart canvas, and these degenerate points form clusters at the corners or junctions of the bars. To localize these clusters, we use dbScan clustering with setting hyperparameters of cluster radius and the minimum number of points in cluster. Visualization of degenerate points allow us to decide the hyperparameters of dbScan clustering more effectively. Once the clusters are identified and localized, we further compute cluster centroid. And then we follow rule-based extraction process to get the height of the bar based on the chart subtypes. The final value represents the bar location and height in the pixel space. Hence, the data extracted after this step is in pixel space. The data extracted with the previous tensor field framework is in pixel space, and to change the pixel space values to the data space, we have to read the values in text represented in the source image. For this, we use text detection and text recognition algorithms in BarChartAnalyzer to localize and extract these textual components of chart like access labels, titles, legend text, etc. In chart images, the text is usually aliased in its raster format and at times is with small font size or heavy formatting or as a single character. We also find varying orientation in a single chart image. Like the title is in a horizontal orientation and the y-axis labels are in vertical orientation. Also, we see labels for x and y axis are sometimes at 45-degree orientation for long tick labels to be fitted in the image. Given these characteristics of text content, we use a predefined deep learning based OCR model named as the craft model for effective text area detection using affinity and region scores. The craft text detection model is used within a unified framework for seeing text recognition for improving the results. Finally, the data values extracted in pixel scale are scaled to its original dimensions or units using the scale factor, computed with the help of the x-axis and y-axis labels. The finally extracted values are saved in tabular format. For both stacked and grouped bar charts, we identify class or series information using the legend to add to the extracted data table. Once we receive the extracted data table, we could now use the table to either reconstruct a chart or generate a textual summary of the chart, along with redesigning the chart itself. The summary that can be used as an alternate text is specifically helpful for the visually impaired to navigate through chart images embedded in a PDF or HTML document. The reconstructed charts are useful in redesigning the color maps, design space, as well as for qualitative analysis of BarChartAnalyzer. The reconstructed plot actually helps us to understand the missing bars or missing values in our extraction process. The reconstructed charts can be helpful to improve the chart color maps for grouped or stacked bars to colorblind friendly color maps, as well as to improve image quality. The redesigning of multi-series chart is a motivating application as they are relatively difficult to interpret. The redesign is helpful in visualizing the data more effectively. We use a well-built sentence structure given in a templatized form in BarChartAnalyzer to highlight features identified from the extracted data table. We consider chart type specific features to generate the textual summary. For instance, in histogram, we include the distribution type, range, and mode information. For bar charts with categorical variables, we check for ordinal variable types like age, day, and date, etc. in the source image and extract the variable-based trend patterns in the chart image. Apart from these, we consider the statistical descriptors such as the range of attributes, correlation between them, standard deviation, and mean values based on the chart type. For experiments and testing BarChartAnalyzer, we have prepared a dataset as a collection of bar chart images downloaded from the internet and bar chart images generated synthetically. We have generated high quality chart images using Python libraries such as Matplotlib. For training and testing the classification, we prepared the dataset using images of various bar charts with horizontal and vertical orientations. The training dataset includes images of simple, grouped, and stacked bars in both vertical and horizontal orientation, as well as histogram images. Our classifier has shown 85% accuracy, and our text recognition model works with 0.95 F1 score on ICDAR 2013 dataset. In this upcoming slide, we showcase a subset of test case images of the horizontal simple bar, vertical grouped bar, vertical stacked bar, and histogram, along with their intermediary results of different components in the bar chart analyzer. The second row displays visualization of the degenerate points evaluated by the TensorField framework. We observe the clusters of degenerate points at the corners of the bar in case of simple and grouped bars. Similarly, we see clusters of degenerate point at the junction of stacked bar and histogram bins. The text detection row shows the text identified in the red bounding box in the given image that is further mapped with the centroid of degenerate point cluster to extract the data value. The extracted data is used here to reconstruct the chart and to generate the textual summary for the given image, as shown in row 4 and 5. In a multi-series chart, color plays an important role in identifying the class or series the data item belongs to. In our algorithm, we use color value only when it is being used for encoding information. Hence, for simple bar charts, we use a default color value while reconstructing the chart. As for simple bars, color does not play any significant role. Finally, to perform a quantitative analysis, we have to compare the extracted values with the source values. And we observe that the extracted values have numerical precision errors predominantly. Hence, to compare the difference between extracted values and the source values, we compute the normalized mean absolute error and the mean absolute percentage error for the synthetic images for which we have the source data intact. The errors are bound in 0 to 1 range. Mean absolute percentage error is commonly reported in a percentage format. We observe that normalized mean absolute error captures our performance better than mean absolute percentage error, as it does not actually augment numerical precision error as much as mean absolute percentage error. Our experiments with different chart images of various design spaces, quality, and larger dataset have helped us to identify the successes and limitations, along with the improvements required in our work. The text detection model limits itself in differentiating characters such as 0 and O, as they are similar looking, and identifying special characters such as exponent or lambda, etc. The TensorField framework misses the small difference in bin height and similarly misses short bars, where the bar height is very close to the axis. As TensorField computation is computed at the pixel level, the image quality affects the degenerate point. Also, our classification model cannot handle variants of bar charts with textures in the bars or hollow bars. Our workflow limits itself in extracting data from hand-drawn bar chart images. Also, our text detection model fails in identifying the text written inside the bars. Here, we achieve the goal of an end-to-end semi-automated workflow for digitizing images of bar charts of different subtypes. We have also generated the training dataset for classification that can be extended further for identifying other chart types, scatterplot, line chart, and pie chart. We extend the use of TensorField analysis to exploit the geometry of bar objects in chart images. For data extraction, we map pixel space data and the data space using the text detection model. Our proposed method also provides a text summary that can be used with text-to-speech conversion tools such as GTTS in Python to assist the visually impaired. BarChartAnalyzer achieves nearly perfect accuracy for high-resolution bar chart images created with standard or minimal formatting available commonly across all plotting libraries. We are considering methods to make the workflow more automated. For example, for now, we are manually setting the parameters for dbScan clustering and manually annotating the images. We would like to automate the process of identifying and localizing degenerate points, as well as would like to use a better method to identify or to extract the chart canvas itself. We thank everyone who has helped us in evolving this idea by providing platform for discussions, reviews, and funds. We would also like to thank Matruchaya and people associated with it to help us understand the difficulties faced by the visually impaired and their requirements. This is the list of key references used in our work. We thank you for your attention and close the talk with the conclusion slide. We will be happy to take any questions.